Hi everyone, my name is Mike MacDonald. Although this video started as a supplement to my previous video titled Einstein Was Right, There Are Local Hidden Variables, it ended up as a complete but shortened treatment of the same, but with a detailed explanation of the spreadsheet. As the title suggests, we are discussing quantum mechanics in the physics sense, also known as quantum theory. More specifically, we will be examining the odd and strange phenomenon known as quantum entanglement, which we will define as two particles that exhibit unusual correlations. Now, the way that you quantify these unusual correlations is through an experiment called the Bell test. It's named after John Stuart Bell, who devised the experiment and offered a fantastical interpretation of the results. The most common type of Bell test is one that uses wave particles of light, known as photons. It is at the heart of the Nobel Prize in Physics for 2022, which went to Alan Aspect, John Clauser, and Anton Zeilinger for, as we see here, experiments with entangled photons. What experiments? The Bell test using photons. And for establishing the violation of Bell inequalities. An inequality is a comparison of two numbers. Where do those numbers come from? You guessed it, a Bell test using photons. So we can see how important this experiment is. It leads to some strange ideas. The fantastical interpretation of the results of this experiment is that it proves faster than light signals. And since nothing is faster than light, we must interpret the universe as not being real. And that's why quantum mechanics is broken. It tells us that what we observe isn't real. It tells us that there are physical influences that are faster than light, but doesn't tell us how that works. It leads to some interesting quotations from physicists who have studied quantum mechanics over a lifetime, such as here and here. So let's get to fixing it. Here's the Bell test experiment. It's shown in this paper by Alan Aspect, one of the prize winners, where he famously states, "We should renounce local realism. The universe is not real." So we want to take a closer look at this Bell test experiment. The experiment requires us to measure the polarity of light. So how do we do that? A quick refresher of polarity would be helpful. Here's the classical model of light as a wave, giving us the orientation of its polarity. In this case, it's vertically polarized because the oscillations of the electrical field are in the vertical direction. Here we see the head-on view of a vertically polarized photon, and this is a horizontally polarized photon. This is the model that I'll use in this video. It's an imaginary circle with a diagonal line through it, with the diagonal line representing the plane of polarity, and the circle representing that line can take on any angle. Where does the straight line model of polarity come from? It comes from a 200-year-old experiment that we can emulate here. We begin with randomly polarized light. In this case, we are looking at the sky. We put up a polarizing filter, we lose half of the light. What light that does pass through the filter is all lined up like a straight line. We prove it by taking a second polarizing filter and lining it up with the first, and observing no diminishment of the intensity of the light passing through both filters. We then rotate the second filter 90 degrees and we observe no light passing through. The intensity of the light passing through both filters is proportional to the angular difference between the two filters. This proportionality is known as Malice's law. Here we see it in its original form on the top, and on the bottom it's in the updated quantum mechanical version. Quantum mechanically, the photons have their own individual polarity, and the difference between that and the polarity of the filter is theta. Note that there are only two possible outcomes. Either the photon passes through the filter, or it gets blocked. The probability that it passes is cosine squared theta, and the probability that it gets blocked is sine squared. That's how we measure the polarity of light, a +1 or a -1. no other direct measurement is available. In the real world, we don't use filters, but rather polarizing crystals. So the photon will go in one of two directions. Again, a binary outcome. So now we know how to measure the polarity of a single photon. It's a +1 or a -1. Looking at the experiment, we have two photons, one going to A and the other to B, also known as Alice and Bob. They pass through their respective crystals and will be diverted in the +1 direction or the -1. Now the B crystal can rotate around its belly button, forming an angle with A's crystal, and we want to keep track of that angle, which we will call theta. When both A and B get a hit, we record the combination. Here are the four possible outcomes we can get. If both Alice and Bob see a plus and a plus, we classify it as a correlation. The same is true if they see a minus and a minus. However, if they see a plus and a minus or a minus and a plus, that will be classified as a non-correlation. This is how we classify the events. We can then calculate the percent that are correlated. Remember, there are only four possible classifications for each measurement: plus plus, minus minus, plus minus, and minus plus. So here's how we're going to do our experiment. We take randomly polarized light, polarize it, and randomly take any two photons and send one to A and the other to B, where they get measured as a +1 or a -1. We then do it over and over with the polarity of the photons changing, but not the fact that the two photons have the same angle. And what we want to end up with is what is known as a correlation probability curve for this setup. At every angle theta, we want to know the percentage of the readings that are correlated. In order to do that, we go back to Malice's law because it gives us a way to make hard calculations. We can construct a simple spreadsheet to give us the results. So let's go to the spreadsheet since it's easier to explain there. So here we have the star of the show. It's the spreadsheet. And let's get oriented. In the upper left-hand corner is our input. Here we see 30, and down here is our output. The input is the angle that Bob's polarizing crystal is at, and the output is the probability of a correlated reading, which is a ++ or a --. We have two stations, Alice and Bob. Alice is always going to be at 0 degrees, her polarizing crystal, and of course Bob is whatever the input is here. Down the left-hand side, we have different angles of photons. These are representative photons. 0 will represent everything from 0 to 5 degrees, and 5 will represent all of the photons between 5 and 10 degrees. So let's take a look at one of them. We'll start with the 60 degrees. We're going to send two photons, one to Alice and one to Bob, and they will both be at 60 degrees. Because Alice is at 0 degrees, it will make an angle of 60 degrees with Alice, and that'll be represented by alpha. If we want to know what the probability that Alice will get a positive reading or +1 reading is, we just take the cosine squared of alpha, and that's 1/4. If we want to know the probability that it's going to be a minus, we just take the sine squared, and that's 3/4. Now, because Bob is at 30 degrees, right here, 60 minus 30 is 30 degrees. And that's the beta. That's Bob's angle with the photon. And of course, we get Bob's probability of a +1 will be cosine squared of beta, 3/4, and for the -1 it will be 1/4 sine squared of beta. If we want to know the probability that both Alice and Bob get a plus and a plus, we just multiply the two plus probabilities. And the same thing for a minus and a minus. We just multiply the two minus probabilities. And the probability that both Alice and Bob will get a correlated reading of a ++ or minus, we just add these two together, and that gives us this 3/8. We can do that for each representative angle of photons, all the way to 90 degrees. and then we simply average them out, and we get the overall probability that we're going to get a plus plus or a minus minus. Now, I only did this to 90 degrees because I know that works. If you want to, you can always take it down to 355, which will be all the way around the circle, and you'll get the exact same answer. So that's what this is all about. We have an input, we have an output. So let's start doing it. We'll put in 0 degrees, and we end up with 3/4. So when Alice and Bob are both at 0 degrees, we will have a probability of a correlation of 75%. We saw at 30 degrees, it was 5/8. At 45 degrees, it'll be 1/2. 60 degrees, it's 3/8. And at 90 degrees, it'll be 1/4. So it's easy to construct this spreadsheet with simple algebra and using Malice's law. We can now construct a curve by plugging in different angles, plotting it, and using an algebraic transformation and the double angle formula to end up with 1/2 cosine squared theta plus 1/4. So with a spreadsheet in high school math, we have the correlation probability curve of performing a Bell test experiment using random photons that happen to have the same polarity. So what's the same probability function if we use quantum entangled photons instead? When you use quantum entangled photons in a Bell test experiment, you end up with a probability curve of cosine squared theta. This is predicted by quantum theory and experimentally verified by our Nobel Prize-winning physicists. This is the unusual correlation. Putting the two together, we can see that the two equations are different, meaning they are two different phenomena. We now rewrite the second equation as 1/2 cosine squared theta plus 1/2 times 1/2. Since we are dealing with probabilities, this means that half the time we will have a solution of cosine squared, and the other half is a 50-50. Meaning exactly half the time, our two little photons look just like quantum entangled photons. We cannot tell the difference between the two. How is that possible? Everything we know about light, everything, is that light is a transverse quantum wave particle. That's a combination of the terms transverse wave and quantum particle. So let's take a look at one. This comes to us from Wave on a String, University of Colorado, Boulder. We are looking at a transverse quantum wave particle. It's a particle because it's located between here and here. In other words, it has a beginning, it has a middle, and it has an end. It's a quantum particle because you can't cut it in half and expect to see two of them. And it's a transverse wave because the displacement is at right angles to the direction of propagation. Additionally, it's in the vertical plane of polarity. In other words, it's a vertically polarized transverse quantum wave particle. This one happens to start at 0 and go up. It starts at 0 and goes up. This is as opposed to starting at 0 and going down. This too is a transverse wave particle in the vertical plane of polarity. However, it is physically different than the previous one. This is where physicists are making their mistake. They treat these two physically different transverse quantum wave particles as being identical, when we can clearly see they are in fact physically different. When you confuse two different states as a single state, you reach illogical conclusions such as faster than light signals and that the universe is not real. Here we see how a transverse quantum wave particle moves. It retains its shape as it propagates. This one is the wave that starts at 0 and goes up. And this is the wave that starts at 0 and goes down. When we take randomly polarized light and pass it through a polarizer and grab a single photon, it can be one of two types. Those that start at 0 and go up, or start at 0 and go down. Additionally, since we started with randomly polarized light, we will end up with a random probability over two possibilities, meaning a 50-50 split. This model introduces you to a local hidden variable. A local hidden variable that was hinted at by Einstein, Podolsky, and Rosen in their EPR paper. It is the local hidden variable that will reveal to us an explanation of the results from a Bell test experiment using entangled photons. If you take a long rope, grab it in the middle, and shake it up and down, you produce two transverse quantum wave particles that are in the same plane of polarity, and they have their wavefronts on the same side of the equilibrium line. We can classify them as entangled. This is also true if we shake it down, then up. So when we take two randomly polarized photons with the same plane of polarity, we actually have four different possible combinations with equal probabilities of 25%. Two of these combinations are just like our model of entangled transverse quantum wave particles, this one and this one. And this occurs 50% of the time. And the other 50%, they are 180 degrees out of sync, this one and this one. And so that's how we end up with 50% of the time our two little photons have the same correlation probability as entangled photons. And the other 50% is a coin toss probability. Now compare this explanation with that of the Royal Swedish Academy of Science, the people who award the Nobel Prize in Physics. Here we see they model photons as beach balls with galaxy lights. The photons appear to be connected with 9 strands of an undisclosed mysterious fibrous material that represents a communication path supporting instantaneous signaling. Keep in mind there is no physical explanation being offered. In other words, it's magic. Folks, this is by definition mysticism and should be vigorously rejected. If you think I'm picking on the Nobel Prize Committee, I'm not. I'm picking on anyone who calls themselves physicists who embrace fantasy as an explanation of natural phenomena. A simple explanation of entangled photons is synchronized waves created at the same time by a single process. This is not unknown. We need but look for examples. They are everywhere. We don't have to refer to quantum entanglement in mystical terms. If you like this video, share it. Thanks.